So today I'm going to talk about a different aspect of quantum dynamics, which relates to the way that isolated quantum systems actually reach thermal equilibrium. Now, this, even for classical systems, is actually a very interesting subfield of study and something which involves many non-trivial concepts. And I'm certainly not going to talk about those in any amount of detail in this lecture, because my focus is going to be on quantum systems. But just to set the stage for what I have to say about quantum systems, I will make a few remarks about classical systems, I'll tell you about some of the sort of important issues in this business of understanding how a system reaches thermal equilibrium, which will also be important in a quantum context. So if you, for the time being, to begin with, consider a classical system. So let's say you have some classical gas. So you have particles which are in some way interacting with one another and are in a box. There's some Hamiltonian, some time-independent Hamiltonian that describes the system. And just to sort of be consistent with the usual setting in which this problem is presented, so let's assume that the box is one which has a fixed volume, doesn't allow any of the particles to escape, and also doesn't allow any energy to flow in and out. So the energy, the total number of particles, and of course the volume of the system are fixed, and this is the standard setting of the microcanonical ensemble. So usually when you learn statistical mechanics in a course, in at least a beginning course in statistical mechanics, it's equilibrium statistical mechanics that you worry about, which is that you already assume that there is something like a state of thermal equilibrium that these particles have reached, and then you try to describe that state. But you can ask about how the system even reaches that state of thermal equilibrium. So for instance, you know that if you were to consider the state of thermal equilibrium for a system like this, then generically, if you take some generic interactions between these particles, then in a state of thermal equilibrium, the density of particles would be uniform, right? Unless there's something special about the box, such that you were breaking the translational invariance or something. What you also know is that if you started the system out in a state in which the density was not uniform, suppose that was your t equal to 0 state, and you let the system evolve for a long time, eventually, because of collisions of these particles with one another, interactions, and also with the walls of the box, and you wait long enough, if the dynamics is sufficiently generic, it will reach this thermal equilibrium state. So it's not like every possible state of this system of classical particles in a box is consistent with thermal equilibrium, meaning with uniform density. You can start from a highly non-equilibrium state, and then, subject to the constraints of total energy, total number of particles, and total volume being conserved, you reach a state of thermal equilibrium. And the interesting thing is that generically, no matter what non-equilibrium state you start with, you would expect to eventually reach the same state of thermal equilibrium. Now, this at first sight might seem very paradoxical, given what I told you earlier about sensitivity to initial conditions and so on. And so you might think that if you started with two initial states which were different from each other, then you would reach, in the two cases, you wouldn't reach anything like the same state, because of the fact that dynamics in general, the interactions in general will give you dynamics which is chaotic. But the point is that the description of thermal equilibrium, what you call the thermal equilibrium state, is not in terms of microscopic variables. So for instance, because this is a classical system, I can actually label each particle. I can call some particle number 2755, let's say. And so when I'm talking about the thermal equilibrium state of this system, I'm not worried about what the position and the momenta of particle 2755 are, okay, or what the position and momenta of particle number 17,968 are. And so if I start the system out in these two initial states which are quite different, and I actually look at the momenta and position of one particular particle for both sets of initial conditions after a certain amount of time, those could be very, very different, right? I mean, that is basically this business of the system being chaotic. However, those are not the variables that you're using to describe the state of thermal equilibrium. What you are using to describe the state of thermal equilibrium, and I'm sure this has been covered many times in this lecture series, including in Professor Kampa's first lecture, is that you're using a bunch of macroscopic variables. And so the whole point here is that what you need in order for the system to reach thermal equilibrium is a notion that there are macroscopic variables, and for instance you can think of a macroscopic variable as, let's say, the number of particles in some reasonably large macroscopic volume in this system, and so the number of particles divided by volume is the density there, so that's a macroscopic variable, or the amount of energy contained in that volume. And so you need quantities like this, and I'm going to generically represent some quantity like that as O. So you need O of t in the limit that t goes to infinity, and some long time limit, in some time limit which is very large compared to some typical microscopic length scales of the system, or perhaps, time scales, or perhaps even time scales that depend on the size of the system, but in some meaningful t going to infinity limit, you want these macroscopic variables to reach some steady state value, and the steady state value is independent of what initial state you started with for the macroscopic variable. Okay, so that is the idea. And so you can ask, well, how does this actually happen? So remember that because you have an isolated system and your dynamics is completely deterministic, the memory of the initial conditions is never lost. So if you looked at the micro state of the system at some long time, in principle, from that micro state, in principle of course being the operative phrase in this expression, you could back out the initial state. Okay. On the other hand, if you were just looking at macroscopic observables, then from the value of the macroscopic observables at some long time, you could not back out the exact initial microstate. Okay? So that's important. So you can ask, well, how exactly does this happen? How exactly is thermal equilibrium reached? How do I show that no matter what sort of initial state I start out with, if I wait sufficiently long, macroscopic observables become blind to that initial state? So let me just, again, so this is a huge field of research in itself. There's a lot that's known, there's a lot that's unknown. There's been decades and centuries of research on this, and it's a whole subfield in itself, which I don't really want to go into. It's a very sort of rich area of research with a lot of very interesting concepts that have to do with things like ergodicity and mixing and classifying different sort of, coming up with a hierarchy of chaotic dynamics and so on. But the one thing which I do want to emphasize, which will also be very important for us in the quantum case, is this, that when we are talking about thermal equilibrium, we are really talking about what happens in some long time limit rather than what happens when you are averaging over a long time. So just to be clear about what I mean by that and why that's important, sometimes in discussions of this topic, you come across the following argument given for why you have equilibrium, and that has to do with something along the following lines, that if the dynamics of the system is such that, given the constraints, let's say in this case the total energy, the number of particles and volume, when you start from an initial state and you look at how the system evolves, then what you will find is that within this constant surface, within the sort of hypersurface of microstates, which have this fixed value of energy and number of particles and volume, if the dynamics is of the sort that will give you thermal equilibrium, you will see that trajectories starting from any initial state will get arbitrarily close to all points within this hypersurface. And so therefore, in some sense, the trajectory starting from any initial point will eventually cover very densely this entire hypersurface. And so if you were to average over that trajectory, right, up to infinitely long times or very, very long times, then it wouldn't matter what the initial state was, because you're basically averaging over the entire phase space. And so that would give you a value that's independent of the initial value. And then you would say, fine, okay, I do that, I agree that that's going to give me a value that's independent of the initial state. But why should I believe that that is actually the value of the macroscopic quantity that I'm going to measure in an experiment or something that I'm actually going to use to characterize the system? And there sometimes the erroneous answer that's given is that whenever you make a measurement, of course you're doing it for some finite amount of time. It's not an instantaneous measurement, so there is a time averaging that's involved. And so the time averaging for over the duration of the measurement is really the same as this time averaging of the trajectory over the entire hypersurface. So it turns out that this is actually not a correct argument, because if you make estimates of how much time it would take for some typical system, even some typical classical system, if you have some basic idea of, let's say, what is the time, because like if you take this and you can ask what is it that is changing the microstate, why do microstates evolve? It has to do with collisions between these particles. And so if you have some idea of what that time scale is, what, let's say, is the average time between collisions of particles, and from that you try to then get an idea of how much time it would take for a trajectory to densely cover this hypersurface, what you will find is that that could actually be much larger than the age of the universe, because you can argue that the amount of time it would take would go exponentially in the number of particles that you have times this microscopic time scale. And so if the number of particles that you have is some 10 to the power of 23 or something, even if your microscopic time scale was like an attosecond, or much, much smaller than that, let's say it was 10 to the power of minus 35 seconds or some absurdly small time scale, because that is being multiplied by exponential of 10 to the 23, you can see that you're going to get a huge time scale. And so clearly that is not the reason. And as I said, it's not like anyone who does classical dynamics and who knows what they're talking about will tell you that's the reason. The actual reason for thermalization in a classical system is a lot more subtle, which actually has to do with intricacies of the dynamics and chaos and mixing and so on. But the important thing that I wanted to emphasize is that when we talk about thermalization, we are actually talking about what happens in this limit, rather than something like O of t dt 0 integrated from 0 to t 1 over t limit t going to infinity. That is actually not what we are interested in. We're actually interested in something which is happening strictly in the limit that t goes to infinity. We want to argue that in that limit you reach some value, these macroscopic quantities reach some value that doesn't care about what the initial state was, and we try to understand what those values are and how they describe thermal equilibrium. Okay. So that's all I wanted to say about a classical system. So what we're going to do is we're going to ask how this happens for a quantum system. So that's going to be basically the topic of this lecture. So one big difference between a classical system, of course there are many differences between classical and quantum systems, but in terms of dynamics, there's actually a couple of very striking differences. So one thing about a classical system is, if you believe that it is sufficiently generic, so again, I'm going to keep using, I have been and I will continue using the word generic a lot, so there's nothing special about the system, there are no special symmetries or anything like that, just consider a very generic kind of system. So if you consider a very generic kind of system, then at least one of the statements of a very strong statement of what it means for the system to thermalize is that regardless of what your initial state is, no matter what initial state you choose, you will eventually in the long time limit reach thermal equilibrium in this sense. Okay? Now, there could be for special systems, special kinds of states for which this does not happen. So, I don't know if Arnab is going to talk about scarce states and okay. But so for instance, this is also a hot topic of research these days, that even in systems which would normally thermalize starting from some initial state, there might be special states which do not end up in thermal equilibrium. But I'm not going to talk about such systems, I'm just going to talk about generic systems. So if you look at a classical generic system versus a quantum generic system, so there is actually one very important difference in the dynamics. So remember that I told you that the equivalent of phase space for a quantum system is the Hilbert space, right? So now if you think of a classical system and you think of its phase space, for instance of this system that I've described here, and so as we've discussed before, the phase space is some 6n dimensional phase space of the momenta, the position coordinates of all the particles. And so if I now look at any point in this phase space of the classical system, that's a microstate. Now the thing with the classical system is that I'm almost certainly guaranteed for a generic classical system that the phase space point is going to evolve as a function of time, right? And you can see that very easily, because if I specify a particular point, I'm specifying the values of the position coordinates and the momentum coordinates of all the particles in the system, right? And so I know that if there's even one particle that's moving, right, at the next instant its position coordinate is going to change, and so obviously this point is going to move. So you can't really, for a classical system, conceive of a system in which a phase space point does not evolve. That is, a microstate does not evolve as a function of time. That will just not happen. But for any quantum system, and so now if you ask for what are microstates, yeah.
But for fixed points, they won't evolve.
For fixed?
For fixed points in your system, they won't evolve even for classical systems.
Okay, all right, good. That's a good point. So, but typically what happens is that those form a set of measure zero. So those are, right. Okay, but that's actually a good point, and it's important that you bring it up because I'll tell you something now for a quantum system. But in some sense, even for a quantum system, the things that I'm going to tell you about could be points which form a set of measure zero. Nevertheless, they are much more important for a quantum system than these kinds of points are for a classical system. So let me just finish what I was going to say, and then I'll come back to this point. Now, for a quantum system, on the other hand, you know that no matter what quantum system you choose, there are going to be so first of all, the equivalent of a phase point in for a quantum system is a state in the Hilbert space. And you know that there are, no matter what quantum system I choose, there is a certain set of states in Hilbert space which will simply not evolve, regardless of what the quantum system is. And so can anyone tell me what those states are, which will not evolve? So the energy eigenstates, okay? And so that's a difference, but now in light of what he just mentioned, you could argue that just like for a classical system, you might have attractors, and so if you start out in an attractor, then the state will not evolve, and but those attractors probably form a set of measure zero. You could maybe even argue this for a quantum system, saying that if you look at the energy eigenstates of the quantum system in Hilbert space, compare it to the entire Hilbert space, all the states in the Hilbert space, that's again a set of measure zero. So isn't it again once again equivalent to what happens in a classical system? And the answer is no. And the reason that the answer is no is that for a quantum system, finally, the evolution of any state in this quantum system depends on these energy eigenstates, because you can write down any state in the Hilbert space as a linear combination of these energy eigenstates. And so the way that the energy eigenstates behave as a function of time actually does strongly influence the way that any other state in the Hilbert space is going to evolve as a function of time, which doesn't necessarily happen for a classical system. So for instance, if you have an attractor, it might attract only trajectories starting from a certain set of initial conditions towards itself. But if you started the system out from some other initial condition, that may not even feel the effect of the attractor. Okay. So that was important, and the reason that that's important is, as it will turn out from what we'll discuss, that the way that a generic quantum system evolves in time and the way that macroscopic observables for a general quantum system evolve as a function of time have to really, that really strongly depends on the properties of the eigenstates of the quantum system, because finally it's the eigenstates that determine the evolution of any state in the Hilbert space of the system. Okay. So I thought I'd just make that point. So with all of that talking now, so let's write down things. So just to specify the problem clearly, so now we're going to consider a quantum system with a time independent Hamiltonian okay. And of course, we know that the way a state evolves is just given by the Schrödinger equation. And we also know that for any such quantum system, you have a set of energy eigenstates. Which are eigenstates of the Hamiltonian with eigenvalues, which are the allowed values of energy. And if you want to know how any general state evolves as a function of time, what you need to do is you first need to write that state, which I'm going to call the initial state, as a linear combination of these energy eigenstates, and you're guaranteed that you can do that because of the Hilbert space structure of this quantum mechanical system. And so you can do this, and then you can plug this into this equation and use this eigenvalue equation to easily argue that psi of t at any time t is summation over n Cn e to the I E n t by h bar, and that's it. That's the way any initial state evolves. I mean, this is just very elementary quantum mechanics. And so if you ask where is the memory of the initial state in this state at time t, so the memory of the initial state is completely contained in these coefficients. So the coefficients that you have in this expansion are the numbers, are the objects which contain a memory of the initial state. And so now if what we want is that we want the expectation value of some macroscopic observable. So again, if you think of the system under consideration to be like particles in a box, it's like for the classical system that we discussed, then a macroscopic observable could be the total number of particles, again, in some volume of this box, or something like that. And so the macroscopic observable corresponds to some operator O hat. And so you can ask about the expectation value of O hat at time t, which is O of t, which is nothing but this quantity. And in order for the system to reach equilibrium, thermal equilibrium, what we want is that we want the limit of O of t as t goes to infinity to be something which is independent of those Cn's, that it doesn't care about the memory of the initial state. And so the question is, how does that happen for a quantum system whose dynamics is generically given by these equations? So what we can do is we can actually write down what O of t is. So you can easily see from everything that I've written on the board that O of t, which is this, and psi of t is given by that expression. So when you plug psi of t into this expression, O of t ends up being the following quantity. So it's summation over m mod cm squared OMM plus where the sum, so there's a single sum here, there's a double sum there, and the sum is over the energy eigenstates of the system, and OMN is the matrix element of the operator O between the energy eigenstates m and n. So what you have in the first term on the right hand side is just a sum over the diagonal matrix elements, and here you have a sum over the off diagonal matrix elements. So as far as O of t is concerned, that's the expression. And so what we have to do is we somehow have to argue that this expression for the right hand side of this expression for a generic quantum system is such that as t goes to infinity, what you have on the right hand side is something which doesn't have any time dependence, meaning that it has a proper t going to infinity limit, and it also doesn't have any dependence on the c's. So that's what it would mean for the memory of the initial condition to be erased, and also for the system to have a proper equilibrium state. And so if you look at this right now at this level of generality, it's by no means obvious that will happen, right? Because you have the c's sitting very prominently on the right hand side. You also have time here, which is sitting in an oscillating exponential, and so it's not at all clear again that when you take time going to infinity, you have a meaningful infinite time limit, right? I mean, like when you have an oscillating function, sine of omega t doesn't have a meaningful t going to infinity limit, neither does cosine of omega t, and here what you have is you have a sum over such oscillating terms, and so there's again, it's by no means a priori obvious that when you add these things up, you will get some meaningful limit as t goes to infinity. So exactly how that happens is what we are going to worry about. Okay, so the resolution to all of this is that it turns out that what comes to your rescue and allows this equilibrium state to actually develop are these objects OMM and OMN. So the matrix elements of the operator in question are the things which are responsible for thermal equilibrium to even exist and for the system to go to thermal equilibrium for a generic quantum state. So these are the things which are going to offset the presence of the Cm's and the Cn's and also this oscillating behavior. So if you look at OMN, so OMN is basically the matrix element of this operator between the eigenstates of the Hamiltonian. Okay, so what I'm going to show you now for most of the rest of this lecture is that if the Hamiltonian in question was something that was a random matrix. So remember that the Hamiltonian is an operator, and you can write the Hamiltonian in some basis, and then it just becomes a matrix of numbers. So when I say that the Hamiltonian is a random matrix, I mean the following thing. So the Hamiltonian is clearly defined in some Hilbert space. If you wanted to write it down as a matrix, then you would have to pick some basis in this Hilbert space. Now for any Hamiltonian in a Hilbert space, there's always a very special basis in which the Hamiltonian has a nice structure, and that is just the eigenbasis of the Hamiltonian, right? So no matter what Hamiltonian you choose, there's a basis in which it's diagonal. But that's a very special basis. So for any Hilbert space, of course, you have an infinite number of possible bases. You have an an uncountably large number of possible bases. So just for the sake of amusement, imagine that you could take all of these bases, put them in a bucket, and you close your eyes and you pick out one basis, and in that basis you express the Hamiltonian. So that's some random basis that you've chosen for the Hilbert space. So the definition of a random matrix is that if you were to, a random Hamiltonian, if you were to write down the Hamiltonian as a matrix on a random basis, its entries would look like random numbers. Okay, so you write out the Hamiltonian on this basis. If the Hilbert space is sufficiently large in terms of its number of dimensions, then of course you're going to have a very large number of entries. You make a list of all of these entries of the Hamiltonian, and then you look at it, and it should look like something which a random number generator would have generated for you. So that's what I mean by a random Hamiltonian. And you might think that this is like a very special pathological kind of Hamiltonian, but what I hope I'll be able to argue, at least to some extent, and which you might also be able to convince yourselves of if you think a little bit, is that this is actually the generic situation, that it's in fact some very special kind of Hamiltonian which would end up not looking random even when the basis that you pick out is some random basis. So the generic situation is actually something where in some sense a Hamiltonian would look random in some random basis that you pick out. That's not entirely a true statement, because towards the end of this lecture we'll see, even though it might look random, there would in general be some correlations between the matrix elements which would manifest themselves in some way. But for the time being, I'm going to ignore all of that. So I'm just going to assume that the Hamiltonian is a random matrix and show you that if the Hamiltonian is a random matrix, then everything that we want does indeed happen. Okay. So suppose H hat is a random matrix. Okay. So which means that if I look at the matrix elements of H in some arbitrary or some random basis of the Hilbert space, so these are the matrix elements, then these will look random. In a random basis for the Hilbert space. Okay. All right. Now, a consequence of this is, so note that this is some random basis, and so H is certainly not diagonal in that basis. So what you could then do is, in that basis, you could obtain the energy eigenstates of the Hamiltonian. And so because the matrix itself looks random, in this basis, even the eigenstates, if you were to write them as column vectors on this basis, those would also look random. So then what will happen is that the eigenvectors in the given basis would also look random. Okay. Now here's the crucial part of what we will require to prove what we've set out to prove, which is that if you now look at this operator O hat, right? So O hat is an operator that corresponds to a physical observable. So O hat is a Hermitian operator because it corresponds to a physical observable. And in particular, there's the basis of vectors in which O hat is diagonal. So O hat is a Hermitian operator, it has its own eigenbasis. And so I can write O hat in its eigenbasis as this. So what this means is that the state I is an eigenstate of O hat with eigenvalue OI, right? And so the point here is that the basis in which Hij looks random, I mean this random basis that we picked for this Hilbert space in which Hij looks random, could just as well be the eigenbasis of the operator O hat, right? So if I had a random Hamiltonian and I had some generic macroscopic operator like O hat, then the Hamiltonian would be expected to look random even in the eigenbasis of O hat. So that's really going to be the crucial ingredient for us. So what that implies is the following, that if you're now looking at the matrix element of O hat, so this is OMN, if you're looking at the matrix element of O hat between eigenstates of the Hamiltonian, so that is going to be equal to summation over OI. Okay, so I can just take this expression for O hat, plug it in here, and then I'm going to get OMN is equal to OI psi I m star psi I n, where psi I m is equal to I m. And so these psi I m's are basically nothing but the coefficients in the expansion of the energy eigenstates of the Hamiltonian in the basis in which O is diagonal. So the eigenbasis of OI, if you were to expand the eigenstates of the Hamiltonian, the coefficients would be the psi I m's, and these are the things which look random. Okay, so is that clear to everyone? All right.
Yeah, so basically what you are saying is that I have a normal Hamiltonian, but if I take a random basis, then Hamiltonian will look random. This is you say, right? But then I don't understand whether, like, if I take a observable and in its eigenbasis, Hamiltonian will look random. Why?
Okay, so I'm just saying that in general, so the other assumption here is, if you like, that when you think of what the macroscopic observables are, which are actually thermalizing, which you're going to use to characterize the thermal state, those are things whose, those are observables whose eigenbases are not in some sense correlated with the eigenbasis of the Hamiltonian itself. Because the Hamiltonian itself is not going to look random in one particular basis we know, which is its own eigenbasis, right? So what we're saying here is that if you look at the eigenbasis of this operator O hat and you compare it to the eigenbasis of the Hamiltonian, then there's really no correlation between those. Those are the kinds of macroscopic operators that we are choosing in order to characterize the equilibrium state.
Okay, so you are saying those are very well, like if I write the eigenvectors of O in the basis of the Hamiltonian,
right,
this will be like very well not a singular.
Right. And so there's a better way of actually quantifying this, which has to do with the following. So just like you know that in a Hilbert space, you can write down any state in the Hilbert space as a linear combination of basis vectors in the Hilbert space, or in other words, you have vectors which form a basis for the states in the Hilbert space. You can also talk about an operator basis. So you can actually write down a basis of operators in terms of which you can express other operators in the Hilbert space. And so in some sense, you're assuming here that whatever it is that you're talking about as the operator or this macroscopic observable to characterize this equilibrium state is concerned, if you were to write it in this operator basis, it wouldn't have a very strong overlap with the Hamiltonian. I mean, physically it's like this, right? If let's say you were looking at the classical problem, the one which we were talking about, and so there we know that E, N and V are conserved. And so clearly you are not going to use E, N and V to determine whether you have reached equilibrium or not, because E, N and V are not changing. So even if you start with a highly non-equilibrium state, when you finally reach the equilibrium state, E, N and V continue to be the same. So you'll use something else which is quite different from E, N, and V, which could be, and by N I mean the total N. So you could look at the density in a small part or the energy density in a small part of the system, and so it's something like that here. Okay, so right. So therefore, the point is that these objects are also going to be random. So that's OMN, and OMN is given by this. And so you can see now that, so OMN has two indices, M and N, and so you can talk about the distribution of these matrix elements. So you can look at how these matrix elements are distributed over the allowed values of M and N. So you calculate OMN for every pair of energy eigenstates, and then you look at that distribution, and that distribution is going to be important for us. So if you look at the distribution of OMN, and you look at the mean of that distribution here, right. So, because these are random, you have some distribution here. And so if you look at the mean of this distribution, given that these are random vectors, you can show, and it's not very difficult to show this, where D is the Hilbert space dimension. So you're basically doing, okay, so I should have been a little clearer. So what you're doing is you're looking at the distribution here. You are looking at the distribution over the space of a set of random matrices, which have this property, meaning that these are all random matrices, and so these are all matrices that would look random in the basis of the eigenbasis of the operator O. And so when you're calculating this kind of distribution, you're calculating the distribution over this set or this sample of random matrices, and then OMN is going to have this form where D is the Hilbert space dimension. And so it's going to be something, so when you do this average over all of these, over the space of random matrices, this is going to be 1 over D times summation over I OI times delta MM. So in other words, when you do this, when you look at this mean over the space of random matrices, then the off diagonal elements have mean 0, and the diagonal elements have some mean that's independent of what M is, right? So the diagonal elements, regardless of what M is, have this value, which I'm going to call O bar, and OMN is equal to 0 if M is not equal to M. Okay, fine. So let's also look at the variance, and we'll see why the variance is important. So if you look at the variance of this distribution, so the
get the factor 1 over D because when M is not equal to N, they are uncorrelated.
right,
when M is
equal to N, then right, and it's normalized, and so it's, yeah, so that's the reason you get the factor 1 over D, exactly, because it comes from the normalization. I mean, I should have mentioned that I'm assuming that these vectors are normalized, right? Okay, so now if I look at the variance of these quantities, so then, so the variance will tell me about the fluctuations in over these mean values. Okay, so if I look at the variance of OMM, so remember that OMM has a non-zero mean. I'm looking at the fluctuations about that non-zero mean. So this is going to be, so let me just call this delta OMM squared. And so from the usual definition of the variance, this is going to be OMM squared average minus OMM average squared. And so I know the expression for OMM from up there. I mean, I know the expression for OMN. I just substitute m equal to n. And so that's going to give me the expression for OMM, and then I can square it, take the average, and subtract the square of the average from it, the usual thing. And so when you carry out this procedure, what you will find, and this is not surprising if you've calculated variances from distributions, you will find that delta OMM squared, so I would urge you to do the algebra as an exercise, but this is going to turn out to be summation over I, OI squared times psi I m to the power of 4 average minus psi I m squared average squared. So that's what this is going to turn out to be. And you know, it's not surprising that it should turn out to be this just from the form of the variance. It just requires a little bit of algebra to show that, you know, the off-diagonal terms go away. Again, so for the off-diagonal terms, again, you're going to have to use at some point this particular fact that when you average over psi I m star psi I n, that gives you a delta m n. So I'd urge you to do this as an exercise. But anyway, this is what it turns out to be. And so now you can ask, well, what is this quantity equal to? And so there it turns out that this quantity, what this is, actually depends specifically on what kind of random matrix I have chosen. So far I just said you let it be some random matrix. But it turns out that there are different classes of random matrices. So for instance, you could have a special class of matrices which look random, but are nevertheless special in the sense that if you were to express those Hamiltonians in some random basis, then the entries would look random, but they would all be real. So a Hamiltonian in general is something that's supposed to be complex Hermitian. So, but you can still think of having a random Hamiltonian which is real symmetric rather than complex Hermitian. So when you express it, you know, in some random basis, it looks real symmetric. So there's a particular name for that ensemble of random Hamiltonians. So that's something that's called the orthogonal ensemble. And further, if the entries look like they have been taken from some Gaussian random distribution, then it's called a Gaussian orthogonal ensemble. And so it just turns out, for reasons that I won't go into, but you might have seen in some of the other lectures, that when your Hamiltonian is random in this way, but still has this special structure that in a random basis it's real symmetric rather than complex Hermitian, then that's because there's some particular symmetry that the Hamiltonian has, and generally that symmetry in physical situations corresponds to having a particular kind of time reversal symmetry. So in some sense, generic systems with time reversal symmetry are described by random Hamiltonians which have this particular structure of being real symmetric and fall in this orthogonal ensemble class. And so for the Gaussian orthogonal ensemble class, you can actually calculate this. And so it turns out that delta O mm squared, this variance for the Gaussian orthogonal ensemble is equal to this. So this is for, and I'll tell you what this is in just a second, for GOE. So GOE is short for Gaussian orthogonal ensemble. and O squared average is just 1 over d summation over I OI squared. On the other hand, if your random matrix ensemble or the random matrix, the Hamiltonian that you're looking at in a random basis looks like it's some generic complex Hermitian Hamiltonian. It has both real and imaginary parts. I mean, the entries in general, aside from the diagonal ones, have both real and imaginary parts, and that the real and the imaginary parts separately look like they are random. Then the system is supposed to belong to something called the Gaussian unitary ensemble. And so Gaussian unitary ensembles, the Gaussian unitary ensemble generally is the ensemble of systems, generic systems, without time reversal symmetry. And so if you do this calculation for a Gaussian unitary ensemble, then it turns out that this is equal to 1 over d times the average of O squared. So there's a factor of 2 between them, which is not terribly important for what I have to say, but this is what you get for GUE or the Gaussian unitary ensemble. There's also another class in this general class of random Hamiltonians, which I won't talk about at all, which is something called the Gaussian symplectic ensemble. And so the Gaussian symplectic ensemble is quite interesting in the sense that if you think of the Hamiltonian, a Hamiltonian belonging to the Gaussian symplectic ensemble, and you look at its entries, the entries look random, but the entries actually look not like regular numbers but what are called quaternions, for those of you who know what quaternions are. And it just turns out that that particular class of Hamiltonians also corresponds to systems with time reversal symmetry, but a time reversal symmetry that's different from the one which corresponds to the Gaussian orthogonal ensemble. And so for actual physical systems, it turns out that the Gaussian symplectic ensemble describes systems with time reversal symmetry but some sort of spin orbit coupling. It applies to systems with spin half degrees of freedom, whereas this one may or may not. Anyway, but that's not particularly important for us, and I thought I'd just mention this for the sake of completeness. But what is important is that regardless of which of these two ensembles you have, there is this dependence of the diagonal matrix elements as 1 over d times the average of O squared. And similarly, if you do a similar calculation for the variance of the off-diagonal matrix elements, and remember that the average of the off-diagonal matrix elements is actually 0. So this variance now is a fluctuation about a 0 value. So delta O m n squared, where m is now not equal to n. So these are the off-diagonal matrix elements. So you can go ahead and you can do this calculation, and when you do it, you will find that, when I say you, I mean using the properties of these ensembles, you will find that this is equal to 1 over d O squared bar for both GUE and GOE. So the difference between GUE and GOE shows up in the variance of the diagonal matrix elements. For the off-diagonal matrix elements, you have that. Okay. So why is this important? So the reason that this is important is that, first of all, you can see that, if you have a large Hilbert space dimension, then because of this factor of 1 over d, the variances become quite small. And so you really have a narrow distribution then of the diagonal and the off-diagonal matrix elements. And so given that, you can write down the following expression, that OMN, so if you look at what the off-diagonal matrix element is, it doesn't even have to be off-diagonal, like just what the matrix element is. So the matrix element can be written as O bar delta mn plus square root of O bar squared by d Rmn, where Rmn are random numbers with mean 0 and variance 1. So let me just explain what I mean by that. So what I mean by this is that because we've argued here that the distribution of these matrix elements is rather narrow, if you now write down what the matrix element is, if the distribution, if it had 0 width, right, if the distribution had 0 width, then all the matrix elements would be the same. So here, of course, that's not the case. The width is not 0. The width does have some dependence on the Hilbert space dimension, and of course, as you take the Hilbert space dimension to infinity, the width gets smaller and smaller. So you can then say that a matrix element is basically equal to whatever is its mean value, which is this, plus some fluctuation about the mean value, which is given by the variance, and that is sufficient in order to describe the distribution, because the distribution is so narrow. And so the mean value, of course, for diagonal matrix elements is O bar. For off diagonal matrix elements, it is 0. And then the variance is, so as far as the variance is concerned, we only need to worry about really the variance of the off diagonal matrix elements, because the mean is 0. For the diagonal matrix elements, in any case, the mean is non-zero. And so we can write it in this way. And so this factor of O bar squared, square root of O bar squared by d is really just coming from taking the square root of this. So what we are saying is that OMN is equal to something like OMN average plus delta OMN. That's what we've written here. And delta OMN is just this, because we don't need to worry about the variance about the mean value. That's not going to be very important for us, because that was, the variance for the diagonal elements, because that's not going, because the mean value is non-zero anyway. And so just to indicate that there is a fluctuation about the mean value, we stick in these random numbers Rmn, which are random numbers of mean 0 and variance 1. So this is basically for random matrices, the structure of the matrix elements of some arbitrary macroscopic Hermitian operator. And so incidentally, this is something which all of you have seen before in Arnab's, which lecture of yours did you, your first, okay, right. So this is really the form of the matrix elements for Floquet systems, in what's called Floquet, what's called the Floquet eigenstate thermalization hypothesis. For non-Floquet systems, so static systems, there's a little more structure here, which I'll get to. But the crucial thing is this. So when I told you that what actually comes to our rescue in terms of an isolated quantum system being able to reach thermal equilibrium, despite the fact that the expression for the expectation value of an operator clearly depends on the CMs and time, meaning clearly depends on the initial condition and time, the thing which allows us to wipe out that dependence is really this structure of the matrix elements. And so we'll see how the structure of the matrix elements allows us to do this. Okay, so having argued for this structure of the matrix elements, let's now look at the expectation value of O of t and what happens to that expectation value in the long time limit. So I actually do have this here, so let me, yeah, very good. So I don't need to write anything new because it's all here. So we are going to use this expression. This is the expectation value of O hat at time t, And now we are going to substitute into this expression what we have derived for the form of the matrix elements. Okay. So if you put in that particular form of the matrix elements into this expression for O of t, this is what you'll end up getting. So this is going to be O bar summation over m mod Cm squared plus Cm star Cn star e to the I, oh no, actually, yeah, no, this is fine, e to the I Em minus En T by H bar Rmn. So that's what this is going to be. And so one thing which you can see is, if you didn't have to worry about the second term, if it was just the first term, then the memory of the initial conditions has gone completely, because the first term we've now written as some O bar, which depends only on the operator, right? It only depends on the eigenvalues of the operator, times summation over m mod Cm squared. But remember that our initial state is normalized. So summation over m mod Cm squared is equal to 1. And so this term doesn't have any knowledge now of the initial conditions. But as far as this term is concerned, it still looks like A, not only does it have some knowledge of the initial conditions through the appearance of these things, but there's also this oscillating time dependence that we have here. So how do we get rid of those? So the way that we get rid of those is that because of the fact that we now have so we've also pulled out something from this sum. So this anything to do with the operator, right, which is the expectation value of O squared. So that has come out of the sum. So what is now in the sum doesn't have anything to do with the operator anymore. It just has to do with the coefficients of the initial state, and of course the energy eigenvalues of the system, and these Rmn's, which are random numbers. And so now you can see that if you go to a sufficiently long time, and so what you have is you now have a summation of over these quantities, right? And this is like a phase, so it's like a phase times all these other things. But what is multiplying this phase is a bunch of random numbers. So then if you go to long times, of course at short times, of course if you take t equal to 0, then all of these are equal to 1. But then if you go to long times, first of all these phases are themselves going to evolve differently. Further, that's amplified by the multiplication with this random number, with the result that as far as this term is concerned, in some long time limit, so this is m not equal to n, so in some long time limit t going to infinity, I can argue that this, so let me write this down and I tell you then where we get this from, that this is equal to something that's 1 over d times square root of d squared. It's of order 1 over d times square root of d squared, or in other words it's of order 1. So how do we get that? So we have these coefficients Cm star times Cn, and so remember that the initial state is normalized, and so therefore as far as Cm star times Cn is concerned, I can pull out a factor of 1 over square root of d from this, 1 over square root of d from that, get a factor of 1 over d, and then then what's left here is again some phase, right, because I pulled out, so the amplitude of Cm is like 1 over square root of d. I've pulled out the amplitude, and so I've got some phase here, I've got some phase here, I've got some phase here. These are, and so for some arbitrary initial state, there is, so these phases again are going to be random, this is random, this is random, all of this is random now. And so if you add up a bunch of random numbers, right? If you have a sum of random numbers, and if you have a very large number of random numbers in that sum, then you know that that sum is basically going to go as the square root of the value, the amplitude, the magnitude of that sum is basically going to go as the square root of the number of terms in the sum, right? I mean, like, you can just think of it, if you like, as a random walk of these random numbers. I mean, like, each term in the sum is being like a step in the random walk. And so when you're adding them all up, you ultimately going to end up getting something like square root of n. I mean, this is the thing which underlies a lot of the basic principles pertaining to the thermodynamic limit. And so here we have d squared terms, right, because it's a double summation. And so we've already pulled out a factor 1 over d, and so it's 1 over d times square root of d squared. And so this object here is something which is of order 1. And so you can now see that O of t is going to be O bar plus this thing. So it's going to be the square root of the variance of O divided by d. And of course, in the limit of d being very large, this is going to be very small. And so your O of t will just go to some value which has no dependence on the initial conditions. And we have taken the limit t going to infinity. Okay. Now, so we've achieved what we set out to do in this case of the Hamiltonian being completely random. But there is something here that I sort of, this might seem plausible to you, but there is something here that we have to be a little careful about in interpreting properly, which will motivate us to do another calculation. So if you go back to the case of the classical system, right, and I sort of talked about how you have to be careful that you're not doing the average over the entire phase space. You're really talking about the long time limit, because of the fact that if you were to do the average over all of phase space, the amount of time it would take for the phase space trajectory to actually densely cover all of phase space could be larger than the age of the universe. Okay? Whereas clearly systems thermalize over a much smaller time scale. Your cup of coffee thermalizes very, very quickly, right? So, but in that argument, when you talk about, and I said, so you're not supposed to average over all of phase space, you're really supposed to look at the long time limit. The long time limit there is really a time which is much larger than some microscopic time scale of the system, right? Like the microscopic time scale for your cup of coffee could be something which is maybe of the order of nanoseconds or something like that. And so it's some time scale which is much larger than that. But even the age of the universe is a time scale that's much larger than that. So if you're just saying that you have to wait for a time scale that's much larger than the microscopic time scale, then you're still not specifying what sort of the upper bound is on this limit that you are taking, that you're not going to wait for the age of the universe, up to a time that's the age of the universe or beyond, because then you're back to a time scale which was like averaging over the whole phase space. So similarly here, when I've just sort of very glibly written down limit t going to infinity, and I've argued that that's what causes all of these things to become random, you can see that if you're looking at just this factor, the one which actually contains the time in it, e to the I em minus en t by h bar, and if I've removed all of these other factors and just looked at e to the I em minus, so if I had, say, just this without the RMNs and the CM stars and CMs, if I had just this and I asked, what would it take for this to look like a sum over random numbers or a sum over random phases? After what time scale would that happen? So clearly, if t is equal to 0, then all of these are equal to 1. So they clearly don't look random, they're all equal to 1. And then as time increases, these would start looking more and more random. But for this to truly look like a sum over random numbers, you need to go to a time scale which is sufficiently large so that it's greater than the reciprocal of the smallest energy difference here. So remember that these are energies of the spectrum of the Hamiltonian. And so it's only when you have exceeded a time scale which is sufficiently larger than 1 divided by the minimum of, or h bar divided by the minimum of Em minus En, that these will look truly random. So by the way, this this whole business of these coefficients looking random, or these phases looking random here beyond a certain time scale, is called dephasing. So it's really through dephasing that you're losing the information of the initial state. But if you considered only this, it would appear that the amount of time it would take for this to dephase is something which would be greater than h bar by minimum of Em minus En. And you can once again we are back to the original problem with the classical system, that if you look at how minimum of Em minus En scales, so minimum of Em minus En is actually going to scale with the 1 over minimum of Em minus En is actually going to scale as the Hilbert space dimension. And if you're going to use this to ultimately model a system of particles, the Hilbert space dimension is going to be exponential in the number of particles. And so once again, we are back, even for this quantum system, we have exactly the same problem, that if the dephasing of this were what was the only thing that was responsible for giving you this order 1, then you would have to wait for a time scale which is going to be exponential in the number of particles that you have in the system. And clearly that is not the time scale over which even quantum systems thermalize. So how do you get around that? And the way that you get around that is actually because you're not averaging over, you're not summing this, but you're actually summing this quantity. So let me just do a calculation quickly and show you how you can argue for that. So the idea is this. So I'm now going to calculate the following quantity, and on the basis of that calculation, I'm going to argue that the system actually does reach thermal equilibrium, or that observable does reach O bar over some reasonable time scale. This calculation is not going to be able to tell us what that time scale is, but it's at least going to be able to argue that that time scale is not going to be something like this. Okay. So how does that calculation go? So the way that calculation goes is this. So I'm going to calculate a quantity sigma O squared, which is defined in the following way. So it's limit T naught going to infinity, 1 over T naught, 0 to T naught, dt, okay, where even though I've written T naught going to infinity here, the T naught that I have in mind, which is practically for a system with a very large number of degrees of freedom, infinite, is this time scale that I mentioned earlier. So this T naught is really like h bar divided by min of Em minus En, but I'm thinking of a system which is in the thermodynamic limit, so that's effectively going to be infinite. And I'm going to calculate this quantity. So you can ask, well, what is this quantity? So what this quantity tells you is, over this interval from 0 to t naught, what is the average deviation of this matrix element of T from its equilibrium value, right? And so if you see that this quantity is very close to 0, then you know that over this interval, it's essentially, over this very large interval, at most times, it's actually at its equilibrium value. And so if it starts out being if it starts out being at some value which is not the equilibrium value and it reaches equilibrium, then it has to reach equilibrium over some time scale which is much smaller than this T naught. Because otherwise, this quantity would not be something that's close to 0, right? Because if it took something of the order of T naught to reach equilibrium, then of course when you do this integral, you would get something which would be of order 1 and not something that's very small. So what I'm going to show you is that this quantity is actually going to be very small, and in fact it's going to go as 1 divided by the Hilbert space dimension. And so in the thermodynamic limit, you can argue that equilibrium is reached in a time scale that is much smaller than this T naught. So that's the idea. Okay, so let's just calculate this. So we have everything that we need to calculate this. So we have this expression for O of t in terms of the matrix elements of O and the CMs and the CNs and everything. So let's stick that in. We also know what O bar is. So when you stick all those expressions into this, into the right hand side, what you'll end up getting is the following expression: 0 to T naught summation over m n p q O m n O p q and C m star C p star C n C q e to the power of I E m plus E p minus E n minus E q T by H bar, this whole thing, minus O bar squared times dt. So you just stick in, this is the expression that we had earlier. O of t is equal to summation over m mod Cm squared O m m plus m naught equal to n Cm star Cn e to the I Em minus En t by h bar O m n. So you just take this, stick this in here, and then open up the square, and this is what you're going to end up getting. So you can work this out again as an exercise in algebra. And all right, so here's now the important thing. So if you look at this, so this is being integrated over time, and so the time dependence is sitting in the exponential, and we are doing an integral of this over time, which is between 0 and some t naught, and t naught is something which is of the order of the reciprocal of the smallest energy difference. And so therefore, for all practical purposes, in this integral over time of this exponential, we can replace this by a delta function. It's like an integral from 0 to infinity. So when you replace this by a delta function, you get delta of Em plus Ep minus En minus Eq, or in other words, the only contributions that you will receive in the sum are from those values of M, P, N, and Q such that Em minus En is equal to Eq minus Ep. So it's only for M, N, P, and Q satisfying this condition that you will receive a contribution from this sum to this quantity. Okay. So now we are going to make one more assumption which is important and which sort of follows naturally in any case from the fact that we've chosen our Hamiltonian to be random, but for actual systems where the Hamiltonian is not fully random, for which there are correlations, this assumption that we are making need not be true in general, but it is important for what we have to say. So even for those systems which are not truly random, you have to assume that they have this kind of structure for this argument to go through. And so that particular assumption is that if Em minus En is equal to Eq minus Ep, then it's either that M is equal to Q. Okay, so this implies that M is equal to Q and N is equal to P, or it implies that the other way around, I guess, that one second. So no, okay, it only implies this. Sorry, it only implies that M is equal to Q and N is equal to P. So this is something that's called the no resonance condition. And so what this means physically, as far as the spectrum of the Hamiltonian is concerned, is that if you schematically think of the spectrum of the Hamiltonian as these its energy eigenvalues placed in some sequence like this is the lowest energy eigenvalue, the next one, and so on, then Em minus En not equal to Eq minus Ep means that if I look at the difference in energies between any two energy eigenvalues, then that difference in energy is not the energy difference between any two other eigenvalues. That the difference in energy between any two eigenvalues is unique in the spectrum. And so this is a no resonance condition. If you do have the same difference between other pairs of eigenvalues as well, then you have what's called a resonance. In principle, of course, in practice, of course, here you could relax this condition a little bit and say that if you have, so for instance, if you have like a continuous Hilbert space, then you're allowed to have resonances of measure 0 or something. But for our argument, it's the simplest to assume that there are no resonances. And just generally in systems, in many body systems in which there is no thermalization, so for instance of the sort that Arnav was telling you about, many body localized systems, one of the things which happens is that you actually do have strong resonances. So having no resonances is in some sense very important for the system thermalizing. And so if we impose this resonance condition, the no resonance condition on what we just wrote down, then it turns out that your sigma O squared, the quantity which we are calculating, with the no resonance condition now becomes the following simple sum: n not equal to m mod Cm squared mod Cn squared mod Om n squared, and which is less than or equal to, so it is bounded by the maximum of mod Om n squared times n not equal to m Cm mod Cm squared times mod Cn squared, right? And each of these is of order 1 over d because the state is normalized, and so therefore this thing is, so what I've written on the right hand side now is max of OMN mod OMN squared times 1 over d, 1 factor 1 over d coming from here, 1 factor of 1 over d coming from there, right? And excuse me, times d squared, because there are d squared terms in this, and so this thing is equal to max of OMN squared mod OMN squared, or in other words, it's bounded by the maximum value of the mod squared of an off diagonal matrix element. And so what we've already seen is that for this, if you look at the distribution of off diagonal matrix elements, then the mean of that distribution of off diagonal matrix elements was 0, and its variance is something that went as 1 over d, right? So therefore, this max of mod OMN squared is something which will go as 1 over d. And so what we've seen then is that sigma naught squared is bounded by something which goes as 1 over d, and so in the limit that d goes to infinity, this is going to 0, or in other words, if you look back to what it is that we were calculating, over this interval, time interval starting from 0, going up to a time scale which is like the reciprocal of the smallest energy difference in the spectrum, over that entire time scale, if you ask how much does O of t, the expectation value, actually deviate from the equilibrium value O bar, right? So that deviation is something that is minuscule. It only deviates from this average value for times which are much, much smaller than t naught, and as a result, that integral that we have performed is something that goes as 1 over d and goes to 0 in the limit, in the thermodynamic limit. So what this argument is telling you is that whatever is the time scale over which you reach equilibrium, that at least has to be much, much smaller than the time scale that's set by the smallest energy difference in your spectrum. So it is not the time scale over which you would have dephasing if you were only summing the phases e to the I em minus en times t by h bar. It's a much smaller time scale, because that time scale is something which is going to be exponentially large in the number of particles that you have, because that's going to go as the Hilbert space dimension. So this is really, in some sense, what underlies thermalization for in a quantum mechanical system, starting from some initial state, that it's dephasing that is important. Dephasing is the mechanism by which you are losing memory of the initial conditions, but that dephasing is something which is happening over a much smaller time scale than the time scale that is set by this energy difference. So by the way, there are names for these time scales. So the time scale that is set by the smallest energy difference, or equivalently, if you have a sufficiently large system with a large number of degrees of freedom, by sort of the mean energy difference, because both of them scale exponentially with the system size, that time scale is something that's called the Heisenberg time of the system. So if you read papers on thermalization in quantum systems, then the Heisenberg time is one of these important time scales. So the Heisenberg time TH is something that goes as, so delta E is like the mean level difference, or also what's called the mean level spacing. But your thermalizing time for a system with thermalizers is much, much smaller than this, because this thing goes as some exponential of n, where n is the number of degrees of freedom. So basically this goes as the Hilbert space dimension, and the Hilbert space dimension is typically exponential in the number of degrees of freedom, regardless of whether the degrees of freedom in question are particles or spins or whatever. So that's the Heisenberg time. Okay.
So Subroto, you, in doing that integral, didn't you choose T0 to be TH?
Didn't I choose T0 to be?
TH. That's not.
Yeah, I mean, but I said that, that in the thermodynamic limit is going to infinity, and so that exponential that I'm integrating over, I can write that as a delta function.
Okay, so no, how does this thing follow that thermalization?
Yeah, so I'm saying that the thermalization time is much smaller than the Heisenberg time.
How does that follow? I mean, this is.
Yeah, so that just follows from the fact that I did this integral from, say, 0 to th of an average that, so 1 over th, 0 to th, and I looked at O of t minus O bar squared dt, and then I find that this is going as 1 over d, which in the limit that d goes to infinity is 0. So what this is telling me is between time t equal to 0 and th, what is the average deviation of O of t from its equilibrium value, right? And this is a positive definite quantity. And so then if this is something that's going to 0, then that would tell you that for, maybe at best a set of measures 0 or something, you have O of t minus O bar is actually different from 0. For all other times, it's actually, effectively equal to 0. And so it can't be, for instance, that this thing takes a time like some alpha times th, where alpha is some finite number, to reach equilibrium, because then this wouldn't be the case. So that's the argument. Okay. So let me just write something down and end. And in the next lecture, I will maybe spend about 10 minutes or so wrapping this up and then move on to open quantum systems. So let me just write down something which is very important and which is a statement of the Eigenstate thermalization hypothesis. Sorry, did someone have a question? No. And Arnav had also written down the statement of the Eigenstate thermalization hypothesis. So we had earlier in this lecture written down OMN is equal to O bar delta Mn plus square root of right. So we'd written down this expression earlier, but these are random numbers, and this is what you would get for what we've considered so far in this lecture, a completely random matrix. But real physical systems are not, even though they thermalize, if you write down the Hamiltonians, they're really not completely random. There are correlations. And so if you had to write down what this would be for a real physical system which thermalizes, then there are modifications to this form. And so let me just write down that modification and just tell you very quickly what those modifications mean, and I'll end. So for real systems that thermalize, you have OMN is equal to O E bar delta Mn plus e to the power of minus s where E bar is equal to Em plus En by 2 and omega is equal to En minus Em, and S of E bar is the thermodynamic entropy is the thermodynamic entropy. I think it's an S E bar by 2 here, right? At energy E bar. Okay. So just a very quick comparison between these two things. So here remember that O bar was equal to 1 over D summation over I OI. So basically it was equal to the average of the eigenvalues of this operator O. Here on the other hand, you can see that we've now brought in an energy. So in this, if you look at this expression, nothing in this expression for the random matrix seems to have any dependence on the energies of M and N, right? You have basically, no matter what M is, the diagonal matrix elements all have the value O bar. And regardless of what M and N are, if you look at the off diagonal matrix elements, they all have sort of the same strength and there's some random variation here. But nowhere do you have any dependence on the energies of M and N, and that is because we considered our Hamiltonian to be completely random. But for systems which actually thermalize, the fact that the Hamiltonians are not completely random, that there are correlations, manifests itself in this particular modification of this form. So there is an energy dependence of O. So when you're looking at the matrix element between M and N, then there is an energy dependence of this diagonal part of the matrix element. So for that, of course, M is equal to N, and so this does indeed depend on the energy. And even the off diagonal matrix element does have a dependence on the energy, the average energy, and the energy difference. So this function is some function of E bar and omega, which is like saying it's a function of E m and E n. And so if you were to look at, so this is what's called the eigenstate thermalization hypothesis, which Ornov also mentioned in his lectures, and I guess other people have as well. I guess Leo Santos also did. So this is the eigenstate thermalization hypothesis. And so it's a hypothesis in the sense that you are hypothesizing that a system which thermalizes has this form for the matrix element of any generic operator. And so what you're saying is that this is a sufficient condition for a system to thermalize. So if you're asking whether a system thermalizes, go ahead and calculate this for generic operators, and if you see that this holds, then you say that the system thermalizes. Okay. Now here you can see that if you were to focus on a window, so M and N are energy eigenstates, right? So suppose you were to look at M and N both belonging to a very small energy interval, then your omega is sort of very close to being 0, and you can sort of effectively take it to be 0, and E bar is just the energy of, is the average energy of these two is just like the energy of one of these, and in that limit you sort of get back this form, because your O of E bar now is just some number, because you're just saying that E bar itself is specified to be a number. You're just looking at the energy eigenvalues within a small energy interval. So one other way in which you can motivate this is to say that for a real system which has some particular eigenspectrum and say some density of states, so you have some density of states as a function of energy, and so the density of states as a function of energy generically is going to look like this for a many body system with some peak somewhere in the middle of the spectrum. Then if you were to divide this, split this up into very small energy intervals, and then choose M and N to only be within a particular energy interval of this sort, then within that energy interval you would actually have OMN having this form. And so the OMN for small energy intervals looks like what you would have for a random matrix. Of course, if you pick M and N to be in different energy intervals, then you have this full structure that you see. And so if you were to look at, so if you ask, well, how small does this energy interval have to be for the structure within that to look truly like a random matrix, what is the delta E for that? So it turns out that even that has a name. So if you were to invert that delta E, you get a time scale, okay? So because you invert an energy, you get a time scale. And so that time scale is something that's called a Thouless time. So for quantum systems, depending on the context, there are different time scales which can be important. We've seen 2 time scales before this is the third one. The first one that we saw was the Ehrenfest time. The Ehrenfest time, of course, is a time scale which exists even for systems with very small, with a very small number of degrees of freedom, like the kicked rotor. But these time scales, which actually have to do, so the Heisenberg time scale is the time scale which corresponds to the smallest energy difference. For many body systems, that goes exponentially in the number of degrees of freedom. So that's another time scale. And then there's this time scale, which is a Thouless time scale, whose inverse is an energy difference over which you actually, the system does look like a random matrix. And this, in some sense, is also related to the time scale over which thermalization actually occurs for the system. You can relate this time scale to diffusive time scales and so on. So the if you have a conserved quantity in your system which diffuses, then there are arguments which you can put forth to say that this Thouless time actually basically goes as something like the square of the length of the system divided by some effective diffusion constant. So, okay, so I'm sorry I went over, so let me just stop here. So in the next lecture, I'll just tell you a couple more things about the eigenstate thermalization hypothesis and then move on to open quantum systems, which will be my last lecture. Thank you.